Hi. So I'm Yoav Weiss. I work at Akamai on our web optimization products. I also work on making browsers faster, working on Chromium and WebKit. And I'm here today to talk about why resource loading on the web is inherently slow and what we're doing in order to make it faster despite that fact. But first of all, just wanted to say that all these illustrations were done by my kid, who's awesome. But if for some reason you're not a fan, let me know. I'll tell her, she'll cry. It will be character builder. That's. So I've been in this industry for a long while now. And first starting out almost 20 years ago, I was working on a web optimization proxy, as one does. And my very first task on the job was to build a proprietary, in retrospect, speedy-like client-server protocol that enables the browser to send multiple requests and get multiple responses over a single connection. And my second task on the job was to integrate an image compression library into that optimization server. And the image compression library was getting really good 2x size reductions on those images. And network bandwidth was extremely scarce at the day, where the top-notch mobile networks were sending data down at 33 kilobits per second, which is not a lot. But when we measured our results, we noticed something odd. Even with those awful bandwidth speeds, a 2x size reduction in images didn't give us similar performance benefits, unless it was deployed at the same time as the client-server proprietary protocol that enabled us to send multiple requests up and responses down. And this was surprising at first, because if we're sending down half the bytes, why aren't we seeing 2 times performance improvements? But on the web, the basic equations of calculating how long it takes to download a site don't really apply. You cannot really treat the contents of a website as bytes you're downloading, because they are discovered progressively and downloaded progressively, rendered progressively, and they continue to download beyond the fact that we consider the site loaded. And one of the main reasons for that non-linearity was that latency had a huge impact on the protocols that we were using. Because the mobile networks at the time were downloading 33 kilobits per second, but they were also doing that with round-trip times of 700 milliseconds. So the overall loading performance was dominated by latency more than it was by bandwidth. And yes, that was a long time ago, and we've progressed a lot in those almost 20 years that have passed, and things got significantly better. So we have significantly better networks. We have improved image formats. We have significantly faster computers, but we also have slower computers. And while latency of cellular networks has decreased significantly, the speed of light hasn't changed much. It still takes a few hundred milliseconds to send light beams from one end of the planet to the other, which is what we're doing when we're sending data over. And the content on the web has evolved significantly over the last 20 years, and from simple text site with images and some JavaScript-based form validation, we now have full-fledged application development platform on our hands. And it's one where you, at least by default, download your entire app every time you want to use it. And on that front, there's also a fundamental difference between the web and previous internet protocols, because other protocols were often establishing a connection, downloading a resource, and then that was it. And that's how the web started. And HTTP 0.9 was a very simple protocol that did just that to download HTMLs. But little by little, we added images and styles and scripts and fonts, plugins, video, audio, and all these different resources now need to be downloaded together in order to create a web page and in order to create the experience that we want to deliver to our users. So I want to talk today about the problems that make resource loading on the web inherently slow, then talk about today's solutions to those problems, and finish the tour by going over tomorrow's solutions to that, because today's solutions are not yet perfect. They still have downsides that we want to address in future protocol improvements. So why is loading slow? What are the problems with loading resources on the web? Well, the first problem, the first thing that the browser does when the user starts loading a page or click a link is the browser needs to start the connection establishment process. That's the first step that is inherently latency bound. The browser has to translate the user visible host name to an IP address, so DNS request and response, which takes 1 RTT, 1 round trip time in that process. Then a TCP connection needs to be established between the browser and the server. That's a process officially called the three-way handshake, but I like Paul Irish's definition of that protocol, which he called the what's up protocol. Basically, the client needs to tell the server that it's interested in establishing a connection. That's the first what's up. And then the server repeats that process and tells the browser that it's ready to start a connection, and only after that the browser can send out data on that TCP connection, and that process takes us another full RTT. And once that is done, TLS has its own version of the WhatsApp protocol, but it's a bit more polite and uptight. So there it's hello. The client says hello to the server says hello to the client. Immediately after that, they exchange keys, which is, I'm not judging. And that whole process takes us another 2 RTTs for TLS and 4 RTTs overall for the connection establishment. The second problem that we hit right after that is the server-side processing. Once the connection is established, the browser sends out a request, and the server needs to figure out what its response to that. And historically, when talking about web performance, before Steve Souders' seminal web performance work, the server-side latency was considered the major problem of web performance. And Steve Souders showed that it's only responsible for 20% of the delays that we usually see, but 20% is nothing to scoff at. And at Akamai, we see median server-side performance times of around 450 milliseconds, which is a lot of time. So this is the second problem. Third is slow start. Once the server has an HTML page that is ready to be sent down, this is when we hit slow start. And slow start is a mechanism that enables the server to start sending data despite the fact that the server doesn't know how much bandwidth it has in order to send that data without overwhelming the network and causing congestion, which is a bad thing you want to avoid. So slow start is a mechanism that enables the server to gradually send more and more data, feel the network out, but it also limits us in the amount of data that we can send down initially. Who here have heard of the 14 kilobyte rule where you have to put in all your critical resources in the initial 14 kilobyte? Cool. So that rule is based on slow start and the fact that the default initial congestion window is 10 packets. So everything beyond those initial 14 kilobytes will take longer than an RTT to download because the server cannot be sure that it can send it without overwhelming the network and sending more than it can handle. The fourth problem is discovery. When the browser starts receiving the HTML, it immediately starts processing it in order to find as soon as possible which other resources it needs to download. And the browser can tokenize the HTML in a streaming fashion, run it through the preloader, and find all the resources that are HTML-based, but that doesn't include all the resources on the web today. There are a lot of resources that are only discovered after creating, like calculating the styles and executing scripts. The critical rendering path means that the browser needs to download the HTML in order to create the DOM, the document object model. And blocking scripts block that DOM from being created because HTML parsing is blocked on them. And CSS is required in order for the browser to create the CSS object model, which together with the DOM is used to create the render tree, which is required for page layout and eventually paint to happen. So basically the user, before the user can see anything on the screen, the browser has to download enough HTML in order to create a sufficient amount of the DOM and download all the blocking CSS and JavaScript before anything can be painted. And as a result of that, browsers have different priorities for different types of resources. Basically, HTML is more important than CSS, which is more important than JavaScript, which is more important than fonts, which is more important than images. But in practice, many implementations have more complex logic, which is depending on the resource position in the document or position in the viewport. But generally, the browser starts downloading the HTML to discover CSS, JavaScript, and image resources. The CSS and JavaScript can often bring along more CSS and JavaScript, and then they can load even more resources. And the result of that is large and convoluted dependency trees where each layer in this tree has to basically wait for the entire, like all the resources in the layer above it to finish executing before the browser will know about this layer and start downloading it. And that is resulting in bandwidth graphs that look like this with many holes in them because there are many occasions where the browser doesn't know that it needs to download more resources because it hasn't discovered it yet. Another problem is queuing. Those of you who travel often are probably familiar with that particular scene where at a security line, there's this one person at the top of the line that just now discovered that you have to take, you have to take out your laptop, take off your shoes, and they are taking their time doing that, and everyone, well-prepared passengers behind them get often irritated by that behavior. So that's a real-life representation of HTTP 1.1 because requests can go out over multiple connections, but each one of those connections can only handle a single request at a time. So if we have multiple images or multiple resources to download, the browser can only download some of them. Originally, it was limited to 2. Nowadays, it's often 6, but it's still a limited number of resources can download per RTT. And that was the reason, that is still the reason why many requests is an anti-pattern. Like having many resources on your page makes it latency bound in HTTP 1.1. And adding more connections relieved some of the pressure there, but it's still, like there is still an inherent head-of-line blocking situation. The sixth problem is contention, where bandwidth contention can happen when you have multiple resources that are downloading at the same time with different priorities. So The result of that is that the lower priority resources are slowing down your higher priority resources. And that happens when, that happens in HTTP 1.1 by definition, but even in HTTP 2, that's not a solved problem, and we'll touch on that later. And finally, the seventh deadly sin of resource loading, bloat. The bigger your resources are, the longer it will take to download them, and the more vulnerable they will be on the network for bad network events if they happen to happen. So resource size definitely still matters. So we have connection establishment, server-side processing, slow start, discovery, queuing, contention, and bloat. So go over that list and see what we can do about each and every one of them, not necessarily in that order. So let's start by talking about queuing. We talked about the perils of HTTP 1.1 and how each connection can only send a single request at a time. And HTTP 2, or H2 as we fondly call it, solves that problem because it enables you to send multiple streams, and each one of those streams is corresponds to a request-response pair, and you can send multiple streams on a single connection, which means that you can send a very large number of requests in parallel and have the server serve you the ones that are ready. And that's a huge difference from the way that H1 was handling resource requests. And if we go back to the airport security line analogy, H2 is like those newer security lines in airports where you have multiple parallel stations where each one can prepare their things. And the first one that is ready goes ahead and passes security. So last time I went through such a security line, I thought of taking a photo for this occasion, but then thought again and decided what will be the consequences of someone like me starting taking photos in an airport security line, and no photo for you, basically. But despite the fact that H2 solves that head-of-line blocking problem, it doesn't magically fix everything. Many people think that by enabling H2, we can now download everything in parallel, and that is not true, because in bandwidth-bound network environments, it's still the network bandwidth that will limit us. H2 enables us to get rid of the latency boundness of the resource download process, but not the bandwidth one. And since H2 changed many things, it also had to rethink priorities, and because for HTTP 1, prioritization was simply done by not sending requests out. The browsers maintained a queue and avoided sending out certain requests in order to prioritize the ones that are sent out. But when H2 came around, it was added a prioritization scheme where the browser sends all the requests to the server, at least theoretically, and the server will order the responses based on their priorities. But HTTP 2 doesn't fix everything. While it's significantly better, it's not yet perfect. One problematic aspect is responsiveness to priorities on the server side. Because H2 doesn't control the transport layer, we end up with effectively having two queues. One is the priority queue in the server, like H2 server implementation, and the other is the TCP queue in the kernel. And because those are two separate queues without much communication between them, it's hard for the server to be very responsive to priority changes or resource cancellations, which can often lead to low priority resources being sent down before high priority ones, just because of the way they reach the server's priority queues. Another problem is that in the event of TCP packet losses, H2 ends up being more vulnerable to that than H1 because we use a single TCP connection for all the resources, and TCP is a reliable protocol, which means that any loss will stall all other communication until that loss is recovered and that packet is retransmitted, which means we basically push down the head-of-line blocking problem from the application layer to the transport layer. And in lossy environments, we can see that H2 is actually performing worse than H1 in some cases. And finally, since there's no shared compression context between the resources, which basically means we cannot compress multiple files together as if they were one, there are still benefits to bundling resources. Bundling resources is a best practice for HTTP 1.1 in order to reduce the number of requests, and we were hoping to get rid of that for H2, but the lack of shared compression context means that there's still benefits to bundling resources together, which is unfortunate. So how are we planning to fix that? Well, because of these issues or inefficiencies in H2, Google has started working on the QUIC protocol a few years back. And QUIC is basically moving the entire stack from transport to security to the HTTP layer, moving all of that to the user space, and so that implementations can have tighter control over what it is that they're actually sending and when they're sending it. So that solves the multiple queues problem and solves the priority responsiveness that H2 has. QUIC also handles packet losses differently and provide different reliability guarantees than TCP. So it provides basically each one of the streams will be delivered in order. So each request response pair will be delivered in order, but other responses will not be impacted if one of the packets were to go missing. So that solves the head-of-line blocking problem in the transport layer. And QUIC is already a deployed protocol in Chrome as well as on various servers, but it's currently not yet a standard, and it's being standardized as part of the IETF in order to provide a reliable, stable version of the protocol that you can deploy on your servers without worrying about updating your protocol version every 6 weeks when a new version of Chrome comes out. And as far as cross-resource compression goes, there's a current proposal for creating H2 level compression that will enable us to compress multiple resources together as if they were a single resource. There are currently some security hurdles in making that actually happen. And as an alternative to that, and to the fact that we need bundling on the web today, is basically better bundling. So there's an emergent web packaging proposal that will enable us to have a file format that enable us to bundle resources together, but then also maintain them as individual resources that can be processed as such. And because JavaScript and CSS processing must be done on an entire file, this will give us significant performance benefits versus creating a huge JavaScript blob or huge CSS blob, which we're doing in today's bundling solutions. Server-side processing is the next big hurdle to loading. This mostly applies to HTML, which is often dynamic, as well as critical. And it's hard to give generic advice on how to speed up your server-side stack because they vary significantly. So I'm not going to try to do that. But traditionally, the advice was to flush early and send down your, like, basically not wait for your database in order to start sending down your static HTML content. So send something to the browser as soon as you can. That can often be problematic in some stacks because if your database call will fail, your entire document can be impacted, and it's not always trivial to switch your document once you started sending the data down. But what we can do is use that server-side thinking time in order to start sending other resources down. And we can do that with server push. Server push is a feature of the HTTP, like the H2 protocol, which enables us to basically send down resources before the browser requested them. And that enables us to put the network connection to good use while we're waiting on the server to make up its mind. And basically enables us to turn bandwidth waterfall, like bandwidth graphs from this to this, so we can ramp up more quickly and fill the pipe with critical resources while we're waiting for the HTML. So when we get, basically it also enables us to ramp up the 14K limit, so ramp up the slow start, the TCP connection slow start before we get the HTML. So in the typical case, we would get the HTML request, wait for the HTML to come in, to arrive, and then start sending the resources down. So at first 14K, and then we can increase it in each passing RTT. But with server push, we can basically start sending that, ramp up that initial congestion window early, and when the HTML comes around, we can send it all down in a single RTT, even if it's significantly larger than 14K. And at the same time, H2 push is not necessarily easy to use. There are still many gotchas which make it tricky to get right in a seamless way. But we have a plan to fix that. One of the main complaints about H2 push, beyond just bugs in the various implementations, is that there's no standard way for the server to know the contents of the browser's cache. So when we're pushing resources, we may be pushing them unnecessarily, and therefore waste the user bandwidth and potentially their time. And Cache Digest is a proposal that can fix that by giving the browser essentially a condensed list of all the resources that it, giving the server a condensed list of all the resources the browser has in its cache. And then the server can decide based on that what resources need or don't need to be pushed without using various heuristics that servers use today. So we've talked about resource discovery and the fact that it's a real problem, real latency, making our resource loading latency bound. Preload is another recent feature that I've been working on, which enables you to tell the browser to kick off a resource download without defining the exact point where that resource will be used. So in a sense, it decouples download from execution and enables us to flatten out the dependency trees by preloading late discovered resources ahead of time. So the browser then, once we use preload, the browser doesn't need to run JavaScript and CSS in order to find the resources that it would have found later. And an important part of that is priorities, because preload enables the browser to know what is the resource that it is downloading by using the as attribute, which can then enable the browser to download the resource in the right priority for that resource type. And one extension to that, one extension to preload is priority hints. That is a recent, very early stage proposal that we're working on that will enable developers to in a way, influence the browser heuristics regarding the resource's priority. Like the fact that a resource is a script doesn't necessarily mean that it's highly important or not. And currently, browsers do all kinds of heuristics based on location, based on whether the script is async or not, in order to try to guess what the priority is. But there are many cases where the developer just knows that this is not an important resource, or that is a critical resource despite the fact that it's an image, because this is, the highly correlates with conversions or whatnot. So priority hints will give us a way to tell the browser what is important and what is not, and help the browser do the right thing. So we talked about connection establishment as something that takes a very large number of RTTs and is inherently latency bound. How can we get rid of that, or alternatively get it out of the way? One potential answer is pre-connect, which enables us to tell the browser either by markup links or as an HTTP header, tell the browser to connect ahead of time to a certain third-party server in order for that connection to be out of the way and be out of the critical path for that resource. Another potential answer is to coalesce the connections that we currently have into a single one. The H2 protocol defines a way for us to coalesce different connections onto the same H2 connection. And the conditions for that are that the certificate will cover, the TLS certificate will cover both hosts, and from a DNS perspective, they will both resolve to the same IP. So that gives us a mechanism that enables us to coalesce connections and avoid multiple competing connections at the same time. Each one of them has to go through the connection establishment process. And in the future, what we're planning to do to improve on that is, like, one approach is switch networking protocols to ones that don't really need connection establishment. So TCP Fast Open TLS 1.3 is one set of, one stack that will enable us to avoid connection establishment entirely, at least for everything that follows up the initial, the client has to create a connection once and then is able to reuse it in the future. Quick is another protocol that enables zero RTT connection establishments, as well as alt service over DNS, which is a protocol extension that will enable browsers to know which servers support or don't support Quick. And talking about solutions for both slow start and contention, I'll talk about them together because the solution is basically one and the same: reduce the number of connections we actually need to use, because every new connection suffers from slow start, and once we have multiple connections, that is a recipe for bandwidth contention. So the immediate solution for that is to avoid domain sharding, which used to be a best practice for HTTP 1.1 to increase parallelism. It's also something that is a high contributor to bandwidth contention, and with H2 we don't really need that. So whenever you can unshard your domains, that is the best way to go. We talked about connection coalescing. We can use that to address this problem as well. One thing that is a big contributor to multiple connections is the fact that non-credentialed connections, so font downloads, fetch API calls, ES6 modules, will nowadays start a brand new connection from a different connection pool, which causes a lot of bandwidth contention issues. The reason for that is privacy, but we're trying to convince the privacy folks that the wins there are not worth the performance hurdle. And one thing that will improve things significantly is secondary search. There's a new proposal that will enable the server to coalesce any third parties or sharded domains onto a single H2 connection regardless of the certificate. Like as long as the server has the certificate, it will be able to coalesce those connections on a single H2 connection. So that will be extremely helpful. And finally, bloat, which is my favorite. Basically, load only what you need is the most obvious thing to do. If you don't need an entire JavaScript library, just download the bits that you need instead of, downloading unneeded code, because it has costs both on resource download as well as runtime. And as far as images go, just use responsive images. I won't go into the details because I could go on and on, but basically make sure that you're just loading what you need. Another recent advancement in compression is Broccoli, which is now supported in all modern browsers and enables you to provide 30% smaller files with the same decompression speed as gzip. So the browser doesn't have to put any more work into decompressing them. It's just on the server side you need to put in more CPU and time, but for everything static, Broccoli is the way to go. Sorry. And one thing we're planning on improving on that front in the future is a compression API that will enable developers to use the browser's native compression and decompression abilities in order to create smarter compression schemes in the browser. So I have said many words. What do you actually need to do? What do I want you to take away from all this? So H2 is a significant improvement over HTTP 1.1. If you're not using it yet, you probably should move to it fairly quickly. Push, preload, and pre-connect are tools that you can use in order to flatten the dependency trees, make sure that your bandwidth is always utilized. You need to use them carefully, but they are good tools to know and try out. You should unshard your domains and coalesce your connections as much as possible. Load only the resources that you actually need. And generally, future improvements are underway to make this whole experience better. Thank you.
I finally got everything I needed.
Here, just go ahead. I will jump on. All right. All right, cool.
So up next, thank you, Yoav, that was great. Come on. I'd say he's coming all the way from St. Paul, Minnesota, but he actually came back from Australia, went home, did his laundry, and then came out here. So next up we have